Hello, everyone! Recently, I visited an unusual museum in Germany where scientists of the Third Reich tried to create a working nuclear reactor more than 80 years ago. While I was there, I became curious. Just how difficult would it be to recreate this under today's conditions? And is it possible to start a uranium nucleus fission chain reaction, say, in your own garage? Well, let's figure it out. You may have seen the Radiocode radiation detector in my videos from time to time. Recently, I got a more advanced model, the Radiocode 110, with a significantly larger detector and extended battery life. The device has become 2.5 times faster than previous models, while still remaining pocket-sized. The new version weighs only 85 grams. For those who don't know, Radiocode is a line of smart radiation detectors for geeks and nerds. The device comes with free mobile apps for Android and iOS, which are regularly updated with new features. The main advantages of the device are its spectroscopy capabilities, which help you determine the type of radioactive source, its high counting speed, now almost 40 times higher than that of standard Geiger tubes, and the ability to build radiation maps. I'll leave a link to the device in the description below. Before we talk about chain reactions, let's first figure out what radiation actually is and how people learn to control it. First, let's take a look at the periodic table and find the radioactive elements in it. That is, those that have no stable isotopes. And here they are, 38 elements, starting with bismuth. The problem is that most of them are synthetic, and only 11 radioactive elements are found in nature. And even then, all of them are products of the decay of the main natural radionuclides, namely uranium and thorium. It's all because the half-life of these elements can exceed 14 billion years, as is the case with thorium, which is comparable to the age of our universe. That's exactly why. Right now, this element is the most abundant among natural radionuclides on Earth. But uranium is less fortunate, since its half-life is 3.5 times shorter than that of thorium. And as a result, there is 3.5 times less of it on Earth. That's if we're talking about the most common isotope, uranium-238. By the way, it was this isotope that marked the beginning of many discoveries related to radiation, which started almost 130 years ago. Back in 1896, Henri Becquerel accidentally exposed photographic film to light in the absence of any light source, simply by placing it near uranium salts. And just 2 years later, Marie Curie introduced the term radioactivity and discovered polonium and radium, which are products of the radioactive decay of uranium-238. Interestingly, radium turned out to be 1,000 times more radioactive, since its half-life was only 1,600 years compared to 4 billion years for uranium. It's also fascinating that in Paris at the Radium Institute Museum where Marie Curie conducted her research, some of the equipment used by the discoverer of radium is still preserved to this day. This glass desiccator, by the way, even turned blue from the intense exposure to gamma rays produced during the radioactive decay of the radium being studied. And the original notes and clothing of the scientist are still kept in lead safes because even after more than 100 years they still emit high levels of radiation. Only copies are displayed in the museum. Radium, by the way, which was famously discovered by the brilliant scientist Marie Curie, was so incredibly radioactive that its compounds could actually glow brightly in the air, thereby producing the remarkable effect of radioluminescence. In addition to radium, Marie Curie also discovered polonium, which was even more radioactive. However, due to its short half-life of only 138 days, traces of polonium on Marie Curie's belongings are now almost impossible to detect. After Marie Curie's groundbreaking discoveries and her receipt of 2 Nobel Prizes, her work was continued by her daughter Irene, who often assisted her mother in scientific research. She decided to continue Rutherford's experiments, in which he had previously irradiated gold foil using alpha particles from a polonium-210 source. In his experiments, he discovered that gold atoms are actually spherical in shape, since they were able to deflect the trajectory of alpha particles, or even repel them backward entirely. This is how, by the way, he created the planetary model of the atom, which was later developed by Ernest Bohr. Instead of gold foil, Irene Curie used aluminum foil. But imagine her surprise when, after being irradiated with alpha particles, the foil itself became radioactive. It turned out that aluminum, like other light atoms, can interact with alpha particles, resulting in the formation of a new element. In the case of aluminum, this was the isotope phosphorus-30. At the same time, 1 neutron was also released. Later on, Irene and her husband Frederick began irradiating other light elements with alpha particles as well. such as nitrogen and boron, obtaining isotopes of other elements from them. For their contribution to science and the discovery of the synthesis of radioactive elements, they were awarded the Nobel Prize in Chemistry in 1935. But most importantly, in addition to discovering artificial radioactivity, Irene and Frederick provided the scientific world with crucial data, based on which other scientists, particularly James Chadwick, discovered and confirmed the existence of the neutron. That is, neutral particles inside the atomic nucleus. In fact, a neutron can be obtained even in almost makeshift conditions, just as the discoverers of this particle did. For this, you need a powerful source of alpha particles, for example, radium chloride powder or elemental polonium. Or for instance, you can use americium from smoke detectors. All of this needs to be somehow fused together or very thoroughly mixed with beryllium powder, after which, in theory, if everything is done correctly, the resulting mixture will emit a certain amount of neutrons. This phenomenon happens because alpha particles, coming for example from an americium source at a very high speed of just 16,000 kilometers per second, powerfully collide with the nucleus of a beryllium atom. And because of its small size, the beryllium nucleus can capture the alpha particle, transforming into the nucleus of a new element with excess energy, which is then released as an emitted neutron. It's also interesting that only alpha particles with fairly high energy can knock a neutron out of a beryllium atom. And for this, only 3 elements are suitable, as they emit a powerful stream of alpha particles. These are radium, polonium, and americium. But thorium, for example, which also emits a stream of alpha particles, as can be clearly seen in a Wilson chamber, cannot interact with beryllium. This is because this nuclear reaction requires alpha particles with high energy. But the alpha particles emitted by thorium have about 20% less energy, which means they cannot overcome the Coulomb barrier and knock a neutron out of the nucleus of a light element atom. The discovery of the neutron in 1932, in turn, gave an even greater boost to scientific progress in the fields of nuclear physics and chemistry, since this particle has no charge, which allows it to more easily overcome the Coulomb barrier, as it is not repelled by the positively charged protons in the atomic nucleus. These ideas, by the way, caught the interest of the Italian scientist Enrico Fermi, who starting in 1934 began irradiating various atoms with neutrons in his laboratory in Rome. It turned out that if the experiments were conducted on a wooden table, the freshly produced neutrons reacted better with heavy atoms than when the experiment was carried out on a metal table. Based on this, Fermi's team concluded that the neutrons could be colliding with the light atoms of carbon and hydrogen in the wood, which slowed down their speed, so they decided to repeat the experiment by passing the neutrons through paraffin. To their surprise, paraffin was also very effective at slowing down neutrons, so instead of just flying past the atomic nucleus at a speed of 14,000 kilometers per second, they would now smoothly approach it at only 2.2 kilometers per second. These neutrons were called slow neutrons, and they reacted very well with increasingly heavier atomic nuclei, all the way up to uranium, after which the experiment stalled a bit because the scientists couldn't figure out whether they had discovered a new element heavier than uranium or if it was something else. But in fact, the experiment at the lab had already been completed by German scientists, namely Otto Hahn and Fritz Strassmann. And here we are, standing next to a replica of the apparatus on which, in 1938, German physicists discovered and confirmed the nuclear fission of the uranium nucleus. It is essentially a primitive Geiger counter, as well as various radioelectronic amplifiers for counting the number of radioactive particles emitted by the radioactive sample per unit of time. In it, these ampules served as the neutron source, containing a mixture of radium chloride and beryllium. The ampules themselves were placed in a block of paraffin where the neutrons were slowed down, and these neutrons, in turn, struck this sample of natural uranium compounds simply lying on the paraffin block. As you probably know, natural uranium consists of 2 main isotopes. These are uranium-238 and uranium-235. When a neutron hits uranium-238, it simply captures it, turning into plutonium-239, which no longer interacts with slow neutrons. But the nucleus of uranium-235, which makes up only 0.73% of natural uranium when struck by a slow neutron, begins to split into 2 other elements. Often, by the way, the fission occurs asymmetrically as shown on this graph. That's why the fission fragments usually have different masses, for example 91 and 142, like krypton and barium. The resulting fragments are unstable isotopes. For example, krypton-91 has a half-life of only 9 seconds, while barium-142 has a half-life of 10 minutes. And since the resulting radioactive fragments have a shorter half-life than uranium-235 itself, they are accordingly more intensely radioactive, which can be easily observed with a simple Geiger counter. To do this, a sample irradiated with neutrons was quickly dissolved, and the radioactive barium-142 was washed out before it had completely decayed. Then, the concentrated sample was placed next to an ionization tube, where the radioactive pulses emitted by the sample were counted. After amplification by the radio equipment, this counter could be used to determine how much more radioactive the sample became after irradiation. If this was confirmed, it meant that successful fission of the uranium-235 nucleus had occurred. In this way, the possibility of splitting the nucleus into parts, releasing a tremendous amount of energy in the process, was discovered. According to the recollections of Lise Meitner, who worked with Otto Hahn in studying uranium nucleus fission, calculations showed that when a uranium-235 nucleus splits, 2 nuclear fragments and 3 neutrons are released, although based on the total mass, the calculations indicated that about half a neutron was still unaccounted for. It turned out that the missing mass is released as energy, which aligns very well with Einstein's equation. E equals mc squared. A replica of the apparatus on which the fission of the uranium nucleus was discovered is now housed in a rather remote museum in the small village of Haigerloch. Its history is quite interesting. The fact is that after the discovery by German scientists, the leadership of the then Third Reich became very interested in the potential of uranium nucleus fission, since the energy produced in the process was simply colossal. Because of this, all publications on uranium in the Third Reich, starting from 1939, were classified, and the research itself was headed by Werner Geiger in Berlin. Interestingly, in just 4 years, the Germans made significant progress in these studies, even managing to achieve a chain reaction of uranium-235 nucleus fission in a small reactor, which, unfortunately, has not survived. However, due to the constant bombings of Berlin by the Allies, it was decided to move the uranium research to the remote town of Haigerloch, located almost 600 kilometers to the south. They decided to install the uranium research reactor in an old cellar beneath a Catholic church. This was how the Germans tried to protect their research from being destroyed by airstrikes. Getting here, by the way, was quite a challenge, since this town really is rather inconspicuous, located in a mountainous area in southern Germany. In 1943, uranium research was officially moved here from Berlin, along with the uranium cubes that German scientists had planned to use to create a nuclear reactor, which would run on heavy water and natural uranium. Today, of course, all these cubes have been replaced with aluminum ones, but they still look quite unusual. However, this reactor had one very significant drawback, really. The thing is, paraffin is not very convenient for slowing down neutrons, since it cannot withstand the high temperatures that occur during the chain reaction of uranium nucleus fission. There is another option, graphite. That is exactly what the Americans used in parallel with the Germans during the so-called Manhattan Project. However, the Germans' graphite contained boron impurities. Because of this, they mistakenly rejected this moderator, believing it was completely unsuitable for these purposes. Instead, they decided to use heavy water, a rather rare and expensive substance, which nevertheless works excellently as a neutron moderator in a nuclear reactor. If you didn't know, heavy water can be obtained from ordinary seawater through a very lengthy process of electrolysis, since regular seawater contains only 0.02% heavy water. That is, molecules in which, instead of 2 hydrogen atoms and 1 oxygen atom, there is 1 oxygen atom and 2 deuterium atoms, the heavy isotope of hydrogen. In terms of its properties, it does not differ much from regular water, although it is still a bit heavier than the latter. Interestingly, if you actually freeze heavy water, you truly get so-called heavy ice, which will quite sink in regular water, whereas ordinary frozen light water will float on the surface. In addition, heavy water is excellent for nuclear reactors using natural uranium, since it hardly absorbs neutrons, which means the reactor fuel does not need to be enriched, something that is quite convenient. The problem was that during World War II, heavy water was not produced in Germany. It was brought in from occupied Norway, where cheap electricity from hydroelectric power plants made it possible to obtain enough heavy water for the German reactor. Unfortunately, the very last barrels of precious heavy water never actually made it to Germany for the German scientists, because almost all of the heavy water that had been produced, along with the essential electrolyzers, was completely destroyed during the daring Operation Gunnercide in 1943. And on top of that, in 1945, American troops discovered the German secret reactor, partially destroying it. Interestingly, before the troops arrived, the scientists managed to hide the uranium cubes, along with their documents, in a nearby field. However, the military eventually found the cubes and sent them to the United States for their own purposes. Part of one of those cubes, by the way, is now in the very museum where 80 years ago German scientists conducted their uranium experiments. By the way, the cube still emits quite a bit of radiation. Unfortunately, most of the documents about the German reactor have been lost. However, it is known for certain that the Germans never managed to achieve a controlled nuclear chain reaction, since no fission products were found in the uranium cubes, nor was any plutonium, which inevitably forms from uranium-238 when it is irradiated with neutrons. Nevertheless, it was the Americans, led by Enrico Fermi, who succeeded in carrying out a uranium nucleus fission chain reaction. The key was that instead of using expensive heavy water as a neutron moderator, they used ultra-pure graphite, which the Germans had previously and mistakenly rejected. The reactor that was started had a power output of only half a watt, but that was already enough to confirm the possibility of a controlled nuclear chain reaction, as well as to produce plutonium as part of the Manhattan Project. By the way, you can learn more about it and about the Soviet nuclear project in my video about plutonium. Yes, of course, all of this is wonderful. But even the not-so-successful German reactors were built with professional equipment and massive funding. But is it possible to make something similar to a reactor in makeshift conditions? In fact, all of this was already tested by the so-called atomic Boy Scout David Hahn. As a child, he was extremely fascinated by radioactive substances and chemical experiments. And by the time he turned 19, he decided to build a kind of nuclear reactor in his shed. The thing is, in 1995, at 19, David decided to build a so-called breeder reactor. The idea was to irradiate thorium with neutrons to obtain uranium-233, which can then undergo fission when exposed to slow neutrons. As a neutron source, David used a mixture of beryllium powder and radium chloride, which he extracted from old clocks with radium-based luminous paint. He wrapped all of this in aluminum foil together with americium sources from smoke detectors to serve as an additional source of alpha particles. Since he didn't have access to a quality graphite moderator or heavy water, he decided to irradiate a mixture of thorium and graphite powder with the neutrons he produced. He planned to extract thorium from old gas mantles, which used to contain thorium nitrate that, when heated, would burn off and form thorium oxide. But since the rather porous thorium oxide was insufficient for the reactor, David decided to reduce this oxide using lithium, thereby obtaining metallic thorium. Irradiating this with neutrons would have a greater effect. Unfortunately, David did not take into account that his entire setup had a low neutron flux and lacked the calculated proportions. Therefore, all his homemade reactor produced was a huge stream of ionizing radiation and maybe a few neutrons escaping from it. Realizing his mistakes and frightened by the high radiation levels, David decided to get rid of his reactor, but unfortunately, he was stopped by the police, along with the radioactive components of the reactor in his trunk. As a result, all the contents of his car, as well as the shed where he conducted his experiments, were disposed of by a special US radiological service. And David and his parents were billed a staggering $60,000 for the considerable costs of safely disposing of the highly radioactive materials. But even if David had meticulously calculated all the precise proportions of his experimental reactor correctly, it still wouldn't have truly worked, because to successfully start a nuclear chain reaction, you would need more than a full ton of thorium to effectively achieve criticality in the reactor and the necessary neutron flux. That's basically the case with all other types of reactors as well, whether they're heavy water, graphite, or even regular water reactors with enriched fuel. The problem lies in the enormous amount of uranium, which is simply impossible for an ordinary person to obtain nowadays. Not to mention neutron initiators, which provide the initial neutron flux needed to start the chain reaction in the reactor. So you really shouldn't try to build a nuclear reactor in your garage, because at best, nothing will come of it, and at worst, you'll irradiate yourself and everyone around you. And on top of that, you'll have legal trouble for handling radioactive materials without a license. Well, I think after watching this video, you've learned how the first atomic reactors were created. And what would happen if you tried to create something like this in your garage under makeshift conditions. But if you enjoyed this video, as always, don't forget to give it a like and subscribe to the channel to learn many new and interesting things.